tells us exactly what's going on here. Great job with that. Okay, so the empirical rule tells us how our data is spread out. And so it says that approximately 68% of your data will lie within one standard deviation of the mean, as long as our data is bell-shaped. So this does not work with symmetric data, but if you have regular bell-shaped data, you should have 68% within one standard deviation of the mean, 95% within 2 standard deviations, 99.7% within 3 standard deviations. So again, that's all written out on your formula sheet. What is not on your formula sheet is this picture. So it looks kind of confusing, but it's actually not. Sorry if you were writing this down. I didn't mean to scroll past. So let's say I gave a test and I said that the average score was a 86% with a standard deviation of 2. Okay, what this is telling me, 68% of my students then should have scored in what window, between what values? It's within one standard deviation. Okay, a standard deviation is 2 in this example. So that would be 2 above and 2 below this. So if the average was 86, then one standard deviation would be between 84 and 88. So to get that first, 86 is your middle, if you're looking at bell-shaped data. So within one standard deviation above or below, that's the 84 and 88. And approximately 68% of my students should have scored in that window.
So if it was standard deviation 1, it would just be 85 and 80.
Yep. Okay, then within 2 standard deviations, I should have 95% of my students. So 2 standard deviations would be 4 above or below, right? So 4 below this would be an 82, 4 above it would be a 90. So approximately 95% of people should have scored between an 82 and a 90. 99.7% is within 3 standard deviations. So if one standard deviation is 2, 3 standard deviations would be 6. So 6 below this would be an 80, 6 above it would be a 92. So this is only for bell-shaped data. Okay, if you have outliers, those percentages aren't going to be accurate. But that's what this is telling us, and that's what that picture is. This picture kind of has it broke down, and the picture is in your book too, but it has it broke down. We said 68% within one standard deviation. So that would be approximately 34 above and 34 below. So right here. Where did the 34 come from? 68 divided by 2, half above and half below. As you go out, my percentage, my confidence is going to get higher. So 95% of my values should be within here. Okay. I added in these extra percentages. So if you think 95 divided by 2 is 47.5 on each end, we've already got 34% in here. So if you did the 47.5 minus the 34, that's where the 13.5 came from. Okay. Within my 3 standard deviations, 99.7% of my data should be there. So again, we added a little bit more. But as we're going out, these are flattening off, so we have fewer and fewer values out on the end. So this is the empirical rule. It only works for bell-shaped data. Questions on that? Let's look at and see. Do they have what they need from that slide? Okay. The following data represents the cholesterol of 54 female patients of a family doctor. All right, I went ahead and I put the histogram up here. Why do you think I did that?
So we know it's bell-shaped.
Right. Is it a perfect bell shape? No, but it is roughly bell shaped. So we can't use this on any set, it has to be bell shaped, that's why I gave you the graph. Part A. Determine the percentage of all patients that have their cholesterol within 3 standard deviations of the mean, according to the empirical rule. So what does the empirical rule say? Within 3 standard deviations of the mean should be what percent? 3 standard deviations is 99.7. Okay, part B, I'm going to give you some actual numbers. So we need to know the mean and standard deviation of this set of data. What's the fast way to find that? Calculator. All right, so I want everybody to go to your calculator and find your mean and the standard deviation for this data. So you'll have to enter it in your L1. I got a mean of 57.41 standard deviation of 0.81. So what this means, if I had one standard deviation, that's like your mean minus your standard deviation and your mean plus your standard deviation. So what would my range of values be? Well, I got between 45.6 and 69.22. Does everyone know where I got those numbers? I did the mean, that's your middle. You subtract your standard deviation to get the low value. You add your standard deviation to get the high value. So if I wanted 2 standard deviations, what would I do? Subtract it twice. So I could even take this number, my 45.6 minus the 11.81. And my 69.22 plus the 11.81. You guys all see where I'm getting these? If I wanted 3 standard deviations, what do we do? Add and subtract one more time. Alright, so let's look at this. I want it to be between 34 and 69.1. So some people can reason through these, some people really need a visual. Our mean was that middle, which was what on this example? What did we say? then we measured off 1, 2, and 3 standard deviations. Here's our first. And we got these two values, that's 45.6, 69.22. Our second one, this was 33.79, A1.03. Our third one, okay, not that you have to do this much work on this problem, but I'm just trying to illustrate it a couple different ways. Either visually with a graph or by writing it down. So I said I wanted you to fall between 34, so that's about right here, and 69.1, so that's about right here. So I'm asking you to fall in this window. Now think about the percentages on that graph we just did. We said 68% had to fall within 1 standard deviation. So that was 34% here and 34% here. Then we said we need 95 within 2 standard deviations. So when we drew the picture, that added 13.5% on each end. So if I want to be between the 33.79 and the 69.22, if I'm in that window, what do I need to do to those percentages? Add them up. We have a 13.5 plus a 34 plus a 34, and we get, so it wasn't just a flat 2 standard deviations. I had basically 1 standard deviation above the mean and 2 standard deviations below. So we just had to add those percentages together. Yes, ma'am.
So on this problem, it doesn't really matter, but like let's say like it was like 61 or something. Like it's not all the way to the end of it, so if we still put the whole percent.
I would just ask you to give me the closest one. So if it's closer to the 69 or the mean, just go with that one. Okay, C. Determine the actual percentage of patients that have their cholesterol between a 34 and a 69.1. So look back at our data. Between 34 and 69, how many points do we have? 1, 2, counting all the points that are between 34 and 69. And how many did I get? 45. So what we have to do, if I want the actual percentage, 45 divided by how many total were there? 54, I believe. So 45 over 54 gives us 0.8333. So it was actually something happened on my slide. There we go. So we approximated by the empirical rule. It said it should have been 81.5%. Our real data was 83.3. Why were they were close? Why were they not exact? Right. Was the original data exactly bell-shaped? No. It was close, so our percentages are close. It's a good rule of approximation, but it is not going to be exact if you have real data. Okay. Now this only applies to bell-shaped data. So if we don't have bell-shaped data, we have Chebyshev inequality. And for whatever reason, I apologize, I copied this out of the back of your book, and it does not have Chebyshev's inequality. I don't know why. It's like the only formula And I meant to add it on here before I made your copy and I forgot. So, if you want to just, on your formula sheet, right under the empirical rule, you can write in Chebyshev. And what it says, this works for any data set. So if I were writing it on my formula sheet, I would probably only put the formula. I probably wouldn't write all the words. If you want to write all the words, you can put it in your notebook. So empirical rule works only if it's bell-shaped. Chebyshev's works for any set of data. And it tells us what percent of our data lies within a certain number of standard deviations. Okay, so again, if you're writing in your notebook, you probably don't need to write all of this. I would probably just write this stuff. So if I wanted to know what percent of my data was within 2 standard deviations of the mean, do 1 minus 1 over 2 squared. And you get 0.75. So it says 75% of your data is within 2 standard deviations. You notice the percentages aren't as high here. Empirical rule, what was the percentage for 2 standard deviations? That was 1. 95. The reason this is going to be lower is because it's assuming your data is not bell-shaped, so it's more spread out. So there's not as much clumped together in the middle. There's more on the ends, so your percentages are lower here. But this is used for any set of data. So let's look at an example of it. All right, so using our cholesterol example, I want to know the percentage of patients that would have their cholesterol within 3 standard deviations of the mean. So all we do, that means our K is 3. So that's 1 minus 1 over 3 squared. And you get 0.8889. So it's 88.89%. Okay, part B, I wanted the actual percentage of patients. So we said within 3 standard deviations, you were between 21.98 and 92.84. All right, let's just find how many points are not there. So any point that's bigger than 92 or smaller than 20. 22 really. Do we have any? We don't have any. So what was the actual percentage? 100. You notice this is less exact. We said it would be at least 88.89. It was actually 100. Again, that's because our data was more bell-shaped. So Chebyshev's was less accurate. Empirical rule was a better approximation. Okay. Last thing I want to talk about is finding a weighted mean, a weighted average. So this is like when GPA is calculated. Okay, A's are worth 4 points, B's are worth 3 points, C's are worth 2 points, and so on. So to find a weighted average, how do you find an average in general? Okay. So to find the weighted average, you multiply each value by its weight, add those together, divide by our total. So it's like an average, but you have an extra step that you have to take something times its weight. For example, let's say for your GPA, you have an A in stats, a B in biology, a C in PE, and an A in history. And I want your GPA. So, how many classes do we have here? 4. So we will divide by 4 at the end. Okay, how much is an A worth? 4 points. So I've got the 4 for my one stats class. I've a B in biology, so that's 3 times my one biology class. A C in PE, 2 for my one PE class, and an A in history. Okay, all of these are multiplied by 1 because we're not doing like college classes that are worth 3 hours each. We're just keeping it simple here for a moment. So if I add those together, we have a GPA of 3.25.
Is that actually how you calculate your GPA?
Mm-hmm.
That's tough.
So basically you can take your number of A's, if you have 5 A's times 4, your number of B's times 3, your number of C's times 2, and then divide by the number of classes. Okay. Alright. So let's do one more example of that and then I'm done. So Bob goes to the weight nut store and creates his own bridge mix. He combines 1 pound of raisins, 2 pounds of chocolate covered peanuts, and 1.5 pounds of cashews. The raisins cost $1.25 per pound, peanuts are $3.25 per pound, cashews $5.40 per pound. What's the cost per pound of the mix? Okay. So let's talk about how will you know what you're dividing by here? The pounds. We have 1 pound of raisins, 2 pounds of chocolate, 1.5 pounds of cashews. So we're going to divide by 4.5. Okay. The raisins cost $1.25 per pound. And how many of those did we buy? Peanuts are $3.25 per pound. And how many of those did we buy?
2.
Cashews are $5.40 per pound, and how many of those do we buy?
1.
So that's how we would set up our weighted average. Get 1585 for the top. It's a cost per pound, so I'm talking about money. I get an average cost of $3.52 per pound. Any questions there? So you